Okay. I think we can start. I'm sorry for I'm sorry for this problem. And today with us we have Dario Coscia. He is a master student here in SISSA in the MATLAB group. And I would like to thank you, Dario, for this talk. You will talk about generative adversarial approach for disorder modeling. So please, Dario.
Thank you, Pierre, and thank you everyone for the patience in these 11 minutes. So yes, I'm sorry for not being there, but for some personal inconvenience, I couldn't join today. And as Pierre already anticipated, we're going to talk about this new reduced order model approach that we have been developing here in SISSA, that it's based on adversarial learning. So Pierre, if you want to go to the next slide, please.
Yes, okay.
Okay. So just an outline of how I'm going to structure the talk. First of all, we're going to review what reduced order models are and why they're important nowadays. Then we're going to switch to generative models. I will briefly introduce what these kind of models are, specifically latent variable models. And then we will combine the two and present in GAROM, which stands for Generative Adversarial Reduced Order Model, which is this new probabilistic approach for computing reduced order model solutions. So you can go to the next slide. Okay, so reduced order modeling, for the one who is are not aware, is a quickly emerging field in computational science. And I think the best way to introduce it is with an example. So go to the next slide. And this is the example that I want to show you. So as you may know, differential equations are basically used to describe natural phenomena. They can be partial differential equation, orderly differential equation, stochastic differential equation. What they all have in common is that they try to explain a system. So here, just make some examples from herd dynamics, weather prediction, car design, or the atomic structure. They can all be explained in terms of differential equation. And this and this mathematical object is very powerful. It has been studied for centuries. And the problem is that we cannot sometimes solve this kind of equation analytically. And we need to solve it if we want to make some prediction about the system. So what we use, and now you can go, are the so-called numerical solvers. They are based on different schemas, like finite difference, finite element, and they're really good. I mean, there have been very smart people studying this kind of solvers. They're able to generalize across different PDEs, boundary, initial conditions, geometries. And what they have really, really good is the fact that they have actually a mathematical framework behind, so we can quantify the accuracy beforehand, let's say. They're actually also stable. But the big problem with this kind of solvers, especially if we want to try to use them in industry, or if we want to solve many times the same system, maybe changing some parameters, is the fact that these solvers are pretty slow. So they tend to have a high computational cost in terms of time. And you can imagine that if we have a parametric PDE, for example, and every time we need to solve this PDE for a different parameter, this kind of solvers can actually sometimes be an issue. So what actually happened is that you can go to the next slide, is that reduced order models have becoming a quickly emerging field. And the basic idea of reduced order modeling is that we want to, let's say, reduce the complexity of the system for performing real-time simulation. The thing that actually it's not possible all the time with numerical solvers. And so I try here to depict what data-driven reduced order models are, and this is what we actually are centering the talk. Basically, they start with a complex model. I think you cannot see my cursor, but anyway, they start with a complex model, and they actually extract some data from some simulations for that complex model, but only few. Why? Because it takes some time, it's slow. And when we have this data, we then use a ROM technique, a reduced order model technique, to generalize. So to be able to build a reduced model from which we can query very fast new solutions. So this is the pipeline. We have the full model, we extract some data, we pass this data to the ROM technique generalizes, and then we get a smaller model from which we can sample solutions really fast. What's the problem now? The problem now, of course, is that differently from numerical solvers, we don't have guarantees on the accuracy, and usually we have a higher error or smaller accuracy. Anyway, the good thing is that we're able to generalize, and this is something that we couldn't do with numerical solvers. And different techniques have been studied in the last decades for, actually more than decades, for ROM, for data-driven ROM. And all of these techniques, which some are based on linear algebra, some are based on neural networks, but what all of these techniques, let's say, have in common is the fact that they are discriminative models. And a discriminative model, what it does is to map the most similar, let's say, input seen during the training to the most similar one during the testing. So as you can see, this could lack some semantic understanding of the data. And so what happens is that, and you can go now to the next slide, some other models actually could be employed. Instead of just looking at discriminative models, we could actually start looking at some generative models. This is a new, let's say, research field. It actually has been studying for a long time in probabilistic machine learning. And the basic idea of generative models is to understand the density of the data. But I will try to make it with an example. So if you can go to the next slide. So I just want to show with this example why we actually would like to perform a generative, let's say, learning instead of a discriminative learning, especially for reduced order modeling. So suppose that we have, let's say, two categories, one that is blue and one that is orange. So the data comes from these two categories. And we ask to build a model that is able to discriminate between this data. So as I said, what a discriminative model would do is to create a boundary between the data. So everything that is going to be on the left is going to be blue, and everything that is going to be on the right is going to be orange. And you can now imagine that if we now have a new point that falls in the right region, it's independently on how far it's from the boundary. The model will always say that that point is orange, 100% sure. And you can imagine that if the point is really far from the boundary, maybe we are less sure about its decision, but the model is pretty sure. And this is a big problem of a discriminative model. And it's the meaning that, I mean, is this problem, it's known as not semantic understanding of the data. So a generative perspective, on the other hand, what it does is to build densities around the data. So it starts a probabilistic, let's say, approach. So we can see now that the blue data define a blue density and the orange data define an orange density. If now we get a point that is really far from the center of the orange density, for example, we know how to quantify how much this is far because it's given by the value of the density. And if we have a very low value in probability, this means that it's less probable that it pertains to that kind of data. And so this is why actually we want to go for generative modeling, because we just don't want to model the most similar input to the most similar output, but we want to model the data itself, understand the phenomena that characterize the data. You can go to the next one. And a famous, let's say, approach for generative modeling are latent variable models. These kind of models have been studied very much. And the idea is that they introduce some hidden factors, are called, in the data. So you can imagine these hidden factors like some factors that the data depend on, but are not accessible. So we cannot actually see these factors. So for example, if you want to obtain a picture of a dog, let's say, these hidden factors could be the background color, the dog position in the picture, the color of the hair of the dog. We use these hidden factors then to obtain a sample, which is an image of a dog. And what actually we want to do now, if we want to perform reduced order modeling, is to convert this framework in a framework that we can use for learning PDEs. And what we do is to start with this latent factor that we call it Z. from a known probability distribution. For example, it could be uniform distribution, Gaussian distribution, beta distribution. And then we pass this variable into a generation process, which you can parameterize by a function, or more than one function, actually, and obtain a sample from the probability distribution of X conditioned on the latent variable Z. And these samples, we hope, and we will show how to do it, follows, let's say, the correct PDE. This is very nice. I mean, we can sample different Z and obtain different samples from the same PDEs, let's say, maybe changing the parameters, we change the solution. But the problem is that the probability theory now tells us that if we want to optimize that kind of probability, P of X, we need to calculate an expectation over Z. We need, in a way, to marginalize over Z. And what's the problem? Otherwise, we cannot apply the likelihood principle. And what's the problem in marginalizing is the fact that if Z increases in dimensionality, we cannot calculate the integral anymore. Even if we try to do a Monte Carlo approximation, it fails. So we actually need different approaches for optimizing that kind of probability distribution. And in literature, we actually have two kinds of approaches based on neural networks, which are prescribed models, as variational autoencoders, and implicit models, as, for example, GANs. Prescribed models, in a sense, define a probability distribution on the model up front. So you actually have the probability distribution already defined before going and optimizing the model. For example, I choose to approximate that P with a Gaussian, something like that. So I define upfront to the model that that distribution is going to be Gaussian and I optimize on the parameters. Implicit models, on the other hand, don't choose any distribution, but they just learn how to sample from the true data distribution. We will go into detail about implicit models later on. So if you can go to the next slide, yeah, please. Okay. And actually recently, because now we have been talking very, let's say, without any practice, recently there's been a group, the one from Vinuesa, that have been playing with this kind of models, latent variable models. Specifically, they use beta variational autoencoders. I will not go into the details about variational autoencoders, but you can think more of it like a probabilistic autoencoder in a sense. And they've been playing with this kind of autoencoder for performing reduced order modeling. And they actually obtain very good results because they obtain near orthogonal representation on the low dimensional basis. And this is really good if we want to interpret the low dimensional representation that they build. And this is obtained because, as I said, by defining a probability distribution, you constrain the hidden factor space, so you constrain the latent space in a sense. And they also obtain very promising results, let's say, in generalizability and in reconstruction error. But the big problem, let's say, that all prescribed models have is the fact that their generalization strictly depends on the distribution that you choose upfront to the model. If you choose a distribution that doesn't explain too well the model will not generalize so well, and you will not obtain the good results. And actually, if you're interested, you can read more about it in the Deep Generative Model book. It's from Jacob Tomkatz. He actually reviewed what are the problems with prescribed models, specifically variational autoencoders. They are known as holes problem, elbow gap. All these kind of problems arise from the fact that the probability distribution is not chosen so well. But actually, if you now think what we want to do, we just would like to obtain samples from a PDE solution, let's say. We don't need to model the probability. We don't want to know the actual density. And so actually, maybe implicit model, and you can go to the next slide, Pierre. So maybe implicit model are more suited for that kind of task. Because as we said, implicit models are used to map, are used to obtain samples from the real distribution data without knowing that distribution. And a very famous, let's say, implicit model is the GAN, which stands for Generative Adversarial Network, that was first introduced by Goodfellow. And basically what it does, as I said, is to, at the end of the day, you give a random noise as input and you get some solution, let's say, as output. And how you can train this model here, I just depict what actually it happens. You pass a variable that here I call Z, that are the hidden factors, to a function, which is a neural network that I call G, that stands for generator. This is parameterized by some parameters theta. And this generator should output some generated data, let's say. And then we have another guy that we call discriminator, that it's parameterized by parameters tau. It's itself a function, so you can think about it as a neural network. And what the discriminator does is taking some real data or some generated data. And then the discriminator has to choose which one is real and which one is generated. So it assigns a probability value between 0 and 1 in the most simplistic form to each input. So you can imagine that if the generator wants to fool the discriminator and the discriminator doesn't want to be fooled, then we start a competition, an adversarial learning between the two. The first one trying to generate, the generator, better and better data, while the second one trying to to distinguish better and better between real and generated. And we can actually formalize this mathematically with this objective function that here I report. I will not go actually into detail because we will not use this kind of GAN, but the idea that what they do is maximizing on the generator ability. So, and at the same time, minimizing on the discriminator ability to distinguish between the two. And actually, these kind of models, GANs, vanilla GANs, have been studied in the reduced order model community very recently in this paper called Reduced Order Fluid Modeling with Generative Adversarial Networks by the Week group. And they actually show that compared to discriminative models, these kind of models are able to understand more the PDE without passing the PDE. And actually they did it by calculating the residual of each solution. And what it turns out is that discriminative model actually cannot learn that kind of behavior, but they just learn to map the most similar input, as I said, to the most similar points seen during the training, while generative model actually learn that the underlying, let's say, function is the PDE, and they learn how the PDE actually behaves. Nevertheless, they actually what they actually also say in the work is the fact that these kind of models are not so good in obtaining, let's say, accuracy as discriminative models. And I argue that the fact that this happens, and this is something that we think, is due to the fact that the discriminator, in a sense, is just outputting a value between 0 and 1. It doesn't tell where the generator is making mistakes. It's too less information from the generator to learn very good, let's say, fields. And so what we actually would like, it's something more like the one that I show in the next slide, which is this kind of GAN. A GAN that for discriminator doesn't just output a yes or no, but it outputs an actual solution. And it turns out that actually there is a GAN that can do this. It's called boundary equilibrium GAN. It was developed by David Berthelot. And differently from an actual GAN that optimizes on the distribution of the data, this type of GAN optimizes on pixel-wise reconstruction loss distributions. What does this mean? This means that instead of outputting a 0 and a 1, the discriminator is modeled as an autoencoder. So what it does is autoencoding perfectly, so outputting a perfect, let's say, image as the input one when the data is real, and outputting an image that is not so good when the data is generated. So in a sense, if we pass to the discriminator a real data from a high fidelity, let's say, solution, the discriminator should output the same, while if we pass a generated data, it should output, let's say, a not so good reconstruction. And by doing this, we can actually show, and we will see how to modify the GAN equations. We can actually start as well as an adversarial learning approach. The generator will try to generate the data as good as possible, and the discriminator will try to reconstruct only the real one and not the generated one. And you can go to the next slide, please, Pierre. But the big problem till now that we are facing is the fact that unconditional GAN, as the one that we saw till now, can only generate data, but we cannot condition the generation process. What does this mean? This means that if we have a parametric PDE, for example, so a PDE that depends on some parameters, we are just able to sample solutions of these PDEs, but we are not able to tell for this specific parameter, I want this specific solution. So we need a way to condition, let's say, this generation process. And to understand what the conditioning mechanism does, I just here make a silly example where X is it's a random variable, and P of X is the probability of sampling a picture of a dog. What actually a GAN would do is sampling some pictures like this. We have different breeds, but we don't want this in general. We want to condition the generation process. So we want something more like on the right. We want picture of dog given the fact that the dog is a German Shepherd. This is just an example, but I think it gives an idea of the fact that what we want. We don't want just solutions, but we want to be able also to say which solution we want. And this leads to, and Pierre, you can go to the next slide, to the thing that we've been developing here in SISSA, and now we're going more into the detail of it, that is this new framework called GAROM, as I said, Generative Adversarial Reduced Order Model. This is a collaboration that I did with Nicola Demo and Gianluigi Rozza. There's already a preprint available. I will not cover all the details about the preprint, but if you are interested after the talk, you can go and check it out. We also have already an implementation on GitHub. You can go on to the next one. And this is the model schematically represented. So you can actually recognize the BGAN framework because the discriminator is an autoencoder and the generator, as I said, is just a neural network. This is an implicit latent variable models because we pass Z as input and then we obtain a solution that is generated data. But what is different is this conditioning mechanism that we apply. And the conditioning is done in the generator with a concatenation between Z and an embedding that we build of the conditioning variables, while on the discriminator is done after we obtain the latent vector representation. You can read this more about the CBGAN paper if you're curious about. The actual thing that I want to highlight is this conditioning mechanism, which is something that I guess is really important. Because conditioning, now we're talking about parametric differential equation, but in general can be done on different stuff. It can be done on different, let's say, shapes. It can be done if we also have some extra parameters or extra time steps. It can be done on that. Every information that we can pass to the generation process to give more information to the generator could be, let's say, put in the conditioning set. But as you can imagine, this kind of conditioning set has some data that are not all in the same form. So we actually need a decoder network that maps the original data, for example, in case we have a shape, maps a point cloud into a vector representation. And this is why we use a specific, let's say, decoder for the generator and the discriminator. It will actually be interesting also to test the importance of this conditioning in the model. So it's something that for sure can be further investigated. Can you go to the next slide, please? And now I just want to say how we actually optimize the guy. And as I said, we use the reconstruction loss, optimize the pixel-wise reconstruction loss as BGAN, which is defined in the following way. If you get a random variable U, the reconstruction loss of U given the conditioning random variable C is given as the absolute value between this U and how the discriminator minus how the discriminator reproduces this U. And the training objective now, the GAN training objective can be derived from the Wasserstein distance between the two losses. And actually what you can find is that it becomes like this, that the discriminator optimizes on LU, where U is an actual, let's say, training data, optimize on minimizing this guy, and then maximizing L of G of Z, so the generated one. And as I said, this is the same as minimizing on real data and maximizing on generated data. On the other hand, what the generator does is minimizing its own, let's say, reconstruction loss, because it wants to generate better and better data. And so you can see now that we have this adversarial training as well. And actually, it turns out that you can obtain very good samples with this kind of big N. There are also some theoretical guarantees on the probability distribution that we'll obtain, but for that I will I suggest you to read more in depth the paper. Finally, there's also this term that it's KT that is used in order to maintain, let's say, a balance between the generator and discriminator during the training, because what it could happen is the fact that the discriminator could become very, very good before the generator starts understanding the whole training process. And so there is a mismatch between the two. So if we want to avoid this mismatch, we need to use this, it's called control balance term, that is from control-based theory. And this, as I said, is used to maintain the balance. Maybe if you want, we can talk about later about it more in depth. You can go to the next one. So we also propose a regularized counterpart that it's called RGAROM, which can be used only in the case the differential equation solution is unique. And we can enforce this uniqueness by adding this regularizer term, that is the difference between the actual data U and the one that we generate. In a sense, what we do is to shrink the variance of the generator. We don't want it for different Z to obtain different U's, but this can be used only in the case the solution is unique. We can go to the next one. And actually now I want to show you some results that we obtained. We tested for 3 different test cases, starting from a simple test case, which is an algebraic problem that you can see in the first row, that it's a Gaussian signal moving inside a square. This Gaussian signal is parameterized by 2 parameters. Then we move to a more complex problem, but still a linear PDE, which is the Greitz equation, which model, let's say, the heat transfer in a cavity. And then we finally get to a more complex nonlinear PDE, which is the Navier-Stokes equation, and we use here the lead cavity problem, which you can see in the last row, changing the Reynolds number from a not turbulent to a turbulent phase. In the first column, you can see the results for the regularized GAROM, so the field that we predict with our methodology. This is the mean field. So actually, we take more samples since it's a probabilistic approach, and we then calculate its mean. And in the next column, you can see the actual field. And as you can see, you can barely see the difference between the two. And this is also evidenced by the last column where we show the L2 error, which is on the order of the 10 to the negative 4, 10 to the negative 5. So a very low error also compared to other simple GANs that are used for reduced order models. And finally, we can also plot the variance. Since I said it's a probabilistic approach, we can actually calculate the second moment. And this is plotted on the third row. This variance term is actually really important because with this variance term, what you can do by manipulating it with some math is to obtain an estimate of the model error. And this can be done by Markov inequality, or if you do some mild assumption of how the errors are distributed with using confidence interval theory. And this is something really good because actually not many data-driven reduced order model can do an error estimate analytically on what they will obtain. Finally, if we have a variance that is really high and we have a unique solution, this also should alarm us that the model has a pure understanding, because as we said, the regularized term should push the variance in 0 because the solution is unique. So if we obtain a very high variance, for sure the model is not understanding the phenomenon. You can go to the next slide, please. And here we also compare to the same problems with different latent dimensions and different methods that are nowadays, I guess, still state of the art. In the gray rows, you can see the L2 relative error on training, while on the white rows, you can see the relative L2 error on testing for different methodology. We have GAROM, regularized GAROM, proper orthogonal decomposition with RBF, POD with neural networks, autoencoders with additive basis function, and again, autoencoders with neural networks. If we start to look just at the training, we can see that basically POD with RBF is the best. I mean, it has the lowest L2 error. It's very good. So everyone would say go for POD with RBF. What's the big problem? The big problem is that if we now go on testing, we see that the POD can increase up to 5 order or 6 order of magnitudes in the error. And this is because we, as we said, the generalizability of this kind of techniques is not so good, maybe due to the lack of semantic understanding. But the problem is that this procedure then it becomes unreliable. We cannot use it. Better is done actually with neural networks, so autoencoder with neural networks or POD with neural networks. Actually, the generalizability there is pretty the same. But what it actually we show is the fact that among all the neural networks, let's say techniques, 7 out of 9 times our procedure actually obtain lowest L2 error, meaning that it is understanding, let's say, more on, is able to reproduce better fields than actual neural networks. And also it's challenging POD in half of the test cases, meaning that even in this preliminary work, we can obtain very good results compared to state-of-the-art models that have been studying for a long time. We can go to the next one. But a thing that we also care about, as we said, is generalizability. I mean, we want to understand how well our network will generalize to test data, and we want to be sure about it. And this thing, it's something that generative models do very well, because as we said, they don't learn a boundary between the data, but they try to understand the density that defines the data. So here what we plot is the average difference distribution for the different test cases. And it is defined as the mean between for a specific parameter for all the field entries between the real one and the generated one. In red, you can see the trained data, let's say the average distribution on the trained data, while in blue on the test data. And as you can see, these two distributions are mostly symmetric, centered in 0, meaning that the error is on average 0, and that the errors that we do on train are the same one as we do on test. They are distributed in the same way. And this is actually something really good, because then we can empirically see that the model is able to generalize pretty well. And as you can see, another evidence that we can empirically see is the fact that if we use a regularized counterpart, the one that should shrink the variance, we also obtain a lower error. So this is showing the first row that we have to 10 to the negative 3 compared to the 1 to 10 to the negative 2 of GAROM. So this is good because in a sense, with a single model, at the end, we can obtain a good generalization across train and test, which is a problematic thing for example, POD. You can go to the next one. And finally, what we actually tested is the so-called model convergence, because sometimes what people say about GAN is that they actually it's very difficult to optimize them. The model doesn't converge at all, or it converges to a specific mode. And so what we actually show here is the results of the training done for 5 simulations across all the tests. So in total, we have 9 different test cases for 5 different trainings. Each one takes about 2 hours. So I'll let you do the math for how long we took on the GPU for doing this. But the thing is, as we can see from the plot, is that all the models here in the dotted line, the average residual, all the models go on convergence. And in general, the variability, which is shown in the shaded area, is not that much across different initialization schemas. You could argue that the Gaussian one, the one on top left corner, actually has a bigger variability, but if you look in that, we are on the order of 10 to the negative 2. Also, if you go back in the previous in some previous slide, no, don't go back. It's the same. If you go back on some previous slides, you could see that also the other methodologies were not performing that well, meaning that maybe the latent dimension 4 is not the best suited for that specific problem. You can go to the next one. And so with this, actually, want to conclude, it was not really technical. I actually avoided to do it because I wanted to show more the potential that reduced order models, but also generative models could have. It's a really, the application of generative modeling to reduced order modeling is a quickly emerging field. There are not many papers out there. So it's an area that we're discovering, but it's really promising. As we said, with the probabilistic approach, we can quantify the uncertainty. This is not something that very many data-driven techniques can do. We are more reliable in a sense because the generalizability is better. As the other papers show, we actually understand better the PDE, the underlying PDE with respect to discriminative models. And so this is a nice emerging field that I guess it's worth more investigating. Also, GAROM, which is a first step towards, let's say, the application of generative models in reduced order models, has many possible, let's say, new research directions, changing, for example, starting from changing the model architecture. In all of these, let's say, tests, we use a very simple neural network for the generator and discriminator. And as we can see, we can still obtain very good results. So maybe if we start using more complex networks based on, for example, UNet or convolutional neural networks, we could obtain even better results. We can understand more on the conditioning, starting to explore different conditioning mechanisms. So this is a prominent area. And if you're curious and you want to actually start digging more about digging more and playing around with this kind of models, we release the code of GAROM, and we also will release a more friendly interface on PINA, which is a software that we use for PDE learning here in SISSA. Or in general, if you want to, let's say, play with data-driven reduced order modeling, you can also consider EasyRB, which is our library that we use for data-driven reduced order models. Thank you.
Thank you, Dario, for the next talk. Now is question time. You can online, you can simply unmute yourself and ask, and if you are in the room, you can maybe come near and ask something. Can you hear Dario?
Yeah. Go ahead.
If you go to the Vinuesa's paper, in that slide you have just shown, that Ricardo Vinuesa's paper, that variational beta variational operator, something in that slide.
Can you also repeat at the end, Pierre? Because I listen voices, but I don't understand questions.
Yeah. So I'm saying, can you go to the Vinuesa's paper, that in that slide, Ricardo Vinuesa's paper on the variational operator before this. Yeah.
Yeah.
So what do you mean by this a near orthogonal representation of low dimensional bases? So in this method, are you computing any modes or bases?
Yes, indeed. They actually compute different modes with their methodology, and what you actually can see is that these modes are orthogonal between each other. They actually have another paper before that, because in that paper they also introduced transformers, but I forgot the name at the moment of that paper, but it's the same group, and you can obtain this, let's say, orthogonality by imposing a normal distribution on the latent space. A multimodal normal distribution on the latent space. So that's how they actually obtain your orthogonal representation. They use a covariance matrix, let's say, that it's fully diagonal.
But is it a nonlinear projection, right? Like you are not projecting on those linear modes, right? Like you are on linear operation. Like as I only know about CNN, it's a projection on a nonlinear manifold. It's not just a linear operation. So I'm saying that these modes or this is it a linear operation? This projection is a linear operation in this?
No. Of course, if you just use one linear layer, let's say it's not. They are not using just one linear layer. They use a more complex, I think, convolutional neural network. But it's not just an autoencoder. That is the point. If you just would use an autoencoder, you don't restrict the space at all, and you would obtain a nonlinear representation. If you use, on the other hand, a variational autoencoder, you are, let's say, constraining the latent space by imposing a probability distribution. The imposition of a probability distribution constrains itself a latent space. You can read this more in the actual, in the autoencoding variational biases, so in the beta variational autoencoder paper. They show why this happens. But the idea is the same, is that if you have a space, if you don't impose any constraint, let's say, you could have all the possible space in the optimization, in the latent space, I mean. But if you impose a constraint, you have to, let's say, the latent space has to be a sample for that specific distribution. So you don't have the full space available anymore.
No, I'm saying finally, I have got some modes from this operation. So then you project your solution linearly on that basis, or it's a nonlinear operation? It means like
no, it's they perform it by autoencoding in a linear way, but then the representation that they have are near orthogonal in the latent space.
Okay, then if you want to do neural network after that, so you project your solution using, say, phi transport U, or you have to go through that same neural, that autoencoding or this operation. Means you get my point, like.
I didn't understand the last question.
This projection is definitely not linear projections like POD and NN, right? It should be.
Yes, exactly.
Okay. So there I am trying to understand this concept of basis. Like I have the idea of this POD basis where I project linearly, but here.
Yes, they try. You're right. I mean, they have a nonlinear dynamics, but they're actually trying to project it in at the end in some linear linear basis by nonlinear, let's say, nonlinear functions. But the reason why they do it, I didn't do it, so I'm not saying that I agree or I disagree. The reason why they're doing it is for interpretability. They want to understand if the model is actually learning the same modes that another, or not. That's why. I mean, I don't say that I agree or disagree. I just reported what they actually did.
And your model also, you come up with some this kind of basis as well, or it just.
I mean, the good thing about our model, especially, you can go to the BGAN. Yes, that one. The good thing about our model is that differently from a most, let's say, simple GAN, like a vanilla GAN, in the decoder, in the discriminator, we actually use an autoencoder network. This means that in that latent vector, we can actually impose some regularization. So we could actually do some regularization to impose near orthogonality. We haven't done it. I think it's something that it could be done, but also you could actually put a variational autoencoder there instead of simple autoencoder. The optimization becomes more tricky, but I know there are people that have done it, especially I think David Berthelot has done in a paper that thing. But of course, with a normal GAN, you could not do it. You need to use this kind of GAN. You need a discriminator model that has an autoencoder if you want to impose some constraint on the latent space. Okay. I hope it was understood.
Yeah, but yeah, maybe we can talk later. Thanks.
Okay.
Just, you are not going over there.
There are other questions?
I've got a question. I don't know if you can hear me.
Yes, Gomo.
Okay. Okay, yeah, I just wanted to know, maybe it's a bit technical, but you spoke about using the Wasserstein distance during the training process. What I was wondering about, because basically, if you use that in order to train, let's say, the discriminator, since you're gonna match probability distribution, basically the important thing is that the distance between the input distribution and the output distribution, it's overall gonna decrease, let's say. But then how can you be sure that you're basically matching each input to the corresponding output, let's say?
Okay, this is a very nice question, actually. First of all, we are not optimizing distributions on data, but as I said, we're optimizing on that L that we saw before. So, and one is basically you can think about it as one for the generator and one for the discriminator, depending on which kind of data that you use. So we have these two distributions. And then that equation actually comes from a bound of the Wasserstein distribution. So we are not optimizing the distribution itself, but we are optimizing an upper bound of that one, hoping to optimize the Wasserstein distribution. It's not that we're optimizing directly that distribution. I mean, it's something more like the elbow concept. When you optimize evidence lower bound in order to optimize the likelihood is the same. So we're not optimizing directly the Wasserstein distribution, the Wasserstein distance, sorry.
Okay, perfect. Just another question.
Yeah.
So basically, if in a predictive regime, you will need to marginalize with respect to the parameters, right? Like in order to have a sort of input, a parameter as an input and a field as an output.
Yeah, in a predicted regime. Sorry, if I understood correctly, you're saying whether if during our predicted regime we cancel out Z, let's say by marginalizing it, right?
Yeah.
Okay, this is interesting because you would say, okay, so it doesn't change anything to actually calculate the expectation before, but we don't marginalize directly because we use samples from X to evaluate an unbiased estimate of the mean. So we use Z, so we use different Z to obtain different samples, but when we have these different samples, we use those samples to calculate the mean. So it's a pretty different thing than calculating directly the marginalization and calculating the expectation once we have more samples. I don't know if you understood it. There was a slide actually that I avoided to put because I thought it was too technical. But I think the important thing is we don't directly marginalize. We use samples from G, and then with those samples we calculate the mean.
Okay, I sort of understood. Thank you very much.
Thank you.
Other questions? You are one? Okay. Yes.
Hello. You can
Hello.
hear me?
Yes, I can.
I have a very basic question. Since you can show the table where you have shown multiple comparison with the results comparison.
This one.
The table.
Next one.
Table where we have.
Table, I don't know what it is.
Next one. Go. This one.
Okay, so here what I can see, if you are choosing the less number of like nodes or means whatever modes, you are getting good results, right? But if you are increasing the number of nodes, so my concern is that if you are considering very less number of modes, are you not losing the physical property of the model?
For the Gaussian problem, you mean?
Means because choosing the less number of nodes itself is saying that you are losing some of the property, right?
Yeah, of course, I agree.
So how so you can say I cannot understand, because if you are choosing very less number, so how you can say it's very good for the so here
Okay.
just saying that could be the proctoral, means the results could be this way. but not the exact. I mean, of course, we are not, but not the very good.
Okay, two things. First of all, we did this test to understand how, by changing the latent dimension on the discriminator, actually the results would be affected. But if you think about it, the generator is the one. The generator doesn't depend at all on this latent dimension. I mean, it depends it indirectly because the discriminator does. But we never said that we're going to obtain a lower representation. We just said that we want to obtain samples. So maybe that's the reason why we obtaining those kind of results. But for sure, I think it's something to be further investigated because this is a preliminary study. And for sure, it's an interesting research direction, understanding what the discriminator, let's say, is learning in the latent space. So I agree with you, which is something to be further investigated.
No, it's good. Yeah. Thank you. Thank you.
Thank you.
Other questions? Maybe the last one. If there are no more questions, we can thank Dario again. Thank you, Dario, and see you next Friday.
Thank you, Francesco. Thank you, everyone.
Bye-bye.
Bye.